Hi, good morning and welcome to a session on temporal difference control. The last session we have seen how to predict temporal difference values and temporal difference model policy. Now we are going to discuss how to control the agent's learning with the help of policy improvement and repetitive general policy iteration approach. The next session we will continue with concept of afterstates. So basically in any control methods there are two types of approaches. One is online control method, second one is offline control method. We have discussed this idea in the previous sessions. In the case of temporal difference model, we are going to discuss both online control and offline control approaches. So here there are some specific names to this online control and offline control approach. The online control method has the name SARSA, State Action Reward State Action. This quintuple is written in the form of short form SARSA. So State Action Return State Action. That is an online control method. That means the value updation will happen within the episode. The second one is Q learning or quality learning. This quality learning is focused on offline control. It will happen at the end of an episode. Okay. The third one is R learning. It has also another name, expected SARSA, but it should have both online and offline version. Finally, we will summarize all these models in the sense of some game theoretical approach. Not our optimization problem like game theory, the real development of game theory. How to decide the agent will move in a game environment. That is our game theory in reinforcement learning. But in optimality conditions and also optimization methods, game theory is a special class of problems. But in all this discussion, the game is simply a decision making environment in which the agent should learn dynamically. It may be different types of problem. It may be some decision problem in engineering, it may be some queuing theory problems. Whatever it is dynamically solve an issue. Okay. First of all, let us discuss online TD control. The short term or short expression for this online TD control is SARSA. The important points on TD control under SARSA. 1. Learn an action value function rather than a state value function. Whether it is online control or offline control, this is the basic principle. Here we are focused on action values, not on state values. Because in many situations, actions are more important than states. The action that matters, the next reward of the agent. That is why this control method is focused on action values, but the prediction method focused on state values. That is the basic difference. Need to trade off exploration and exploitation. Whatever control options you are going to develop, remember you should have a policy which satisfies the exploration exploitation dilemma. How to explore different actions, how to choose best actions. There should be a mix of this choice, exploration and exploitation. That mix should be proper, then only the proper learning will happen in a environment. Okay. The last one is on policy and off policy approaches. There are two types of approaches in TD control that we have seen in Markov control and also in the case of our dynamic programming approaches. To understand the Q value updates, we can look into this plot. This plot explains QSA and Q of S dash A dash. Here we are writing iterative formula. That is why we specify ST1, ST, etc. For convenience, I denote the current state ST by S and the action AT by A. So this can be represented as Q of SA. It's also Q of SA. Okay. Then return RT plus 1, that means return for the action from state ST to ST plus 1 with the action AT. It is denoted by small a in this representation because this is more general. Now you just look into this plot. This is the current state ST. It is represented by S. Then there are many possible actions. You can select any of these actions and denoted it as A. Here it is AT. Okay. This choice may be a greedy policy or epsilon greedy policy. That is your choice. If it is an MTP, we can use expectation concept, expectation value of these different policies, the different actions. Then we can select the average. That average value, we choose the average value. Another option is we break the tie arbitrarily. There are 3 possible actions. You choose arbitrarily one action. Okay. Anyway, you just calculate an action value for this action A. The chosen action is A here, the central action. Then you have to calculate the action value for this A, that is Q of STA. Initially we assume that Q of STA is equal to 0 or any random value, that is Q of STA. That is assumption. Now this value is updated. It is updated with this operation. Alpha is a learning rate. Then RT plus 1, that is the immediate return obtained by choosing this action. It is denoted by R here. Then gamma is the discount factor. How the learning from this state is transversed into this state. Okay. Then Q of ST plus 1 comma AT plus 1. At this new state, there is an action. AT plus 1 is chosen. It is denoted by A dash. For example, we can choose this one as A dash. The choice is again based on some policies like epsilon soft or greedy policy. Epsilon soft or greedy policy, we can choose this action. Then how we update this action value? This action value is equal to the existing action value plus the learning rate into this reward plus the action value corresponding to the chosen action from the state S dash. Q of ST plus 1 comma AT plus 1 minus the state action value Q of SA. This is called our temporal error. Our aim is to minimize this temporal error and we got an update for Q of STA. This is the diagram. But important to remember, we are not updating the state value, we are updating this action value. So in Richard Sutton's approach, this action value give more importance than this state value. It also in the plots. You will see in later. So this is the basic idea of choosing an action from an existing state, then consider the reward for that particular action, then calculate the state value, the action value corresponding to a state S dash with the choice of another action A dash. That choice is again based on an epsilon greedy or epsilon soft policy. If you are choosing epsilon greedy or epsilon soft policy, automatically the exploration aspects can be covered. If you choose just greedy approach, then automatically exploitation approach will cover. So in game theory, we mainly focused on this exploration and exploitation in a mixed way. Then only it creates some thrill in gaming. Okay. Now we look more into SARSA. We are using the same equation, but how the update will happen, that make difference in SARSA and Q-learning. In SARSA, what happened? The agent follow the action under given policy. That is very important. The agent always follow the trivial action. Whatever be the policy we have given to the agent, the initial policy. Then iterate over all states. It moves on all states in the environment. In infinite number of episodes, it repeats as many times as possible so as to ensure the convergence of state values. Then in each iteration in an episode, the actions are updated using epsilon soft policy. So that is a very important thing, because it is an on policy control. The action values are updated within the episode, and therefore the next time within the episode, the next iteration will make use of the new policy, the new selected action. So it is updated incrementally within the episode. Okay. So Now this is our Sutton's approach. In Sutton's textbook, here action values are very important. So these dots are action value. That is why I make it the top. This action value at a particular state is updated with action value in the next state. So action value is updated using action value in the next state. That is SARSA. Okay. Then this is a pseudo code for SARSA. Algorithm parameters, step size alpha in 0, 1 for small epsilon greater than 0. This epsilon is chosen for our greedy algorithm. Then alpha is learning rate. The learning rate may be any value in between 0 and 1, but excluding 0 and including 1. Initialize Q of SA for all states in the given environment, and for all action A of S arbitrarily except the terminal action. The terminal state actions give 0 values. In spite of number of actions at the end state, all the action will have the value 0. Okay. Then loop for each episode. Initialize S. We stand on or fix on a particular state. Choose action A from S. We choose an action using policy derived from Q. That may be epsilon greedy. We can apply some exploration. We can choose any actions from that. It need not be the action with the maximum Q value. We just choose any action, either using exploration approach or exploitation approach. Okay. Then loop for each step of an episode. We fix each state yes, then move on next state until that episode is completed. Okay. Take action A, observe R S dash. You choose an action A and just observe its return and next state. Choose A dash. A dash means action from the next state S dash using policy derived from Q. Here again we use the policy. That policy may be epsilon greedy. That means the next state action can be selected using exploitation or exploration approach. Okay. Then the update Q of SA, the current state value Q of SA with action A is replaced or updated with current state action value plus alpha into the reward for that action plus our discount factor gamma into Q of S dash A dash. Q of S dash A dash is selected according to this policy minus the existing state action value of the state S under the action A. We repeat it. Before that, remember this S is updated with S dash. We just move on to next state, and also the action is updated with the A dash. You change the action also. That means you include the selected action into our policy, as in the case of Monte Carlo iteration. So what happened? The policy changed. Policy changed within the episode. The next iteration in that episode used this new action in the policy. So it's iteratively improved. Okay. So this repeat until S leads to the end terminal or terminal state. So it will run on all possible episodes so as to get a steady state values for all the states in the environment. That means the system becomes stable. In that case, the state values are saturated or stable. In that case, our policy is optimal. Okay. Then Q learning. You just compare Q learning with SARSA. In SARSA, we make the update within the episode, but in Q learning, we make the update at the end of the episode. The formula difference is here. Instead of Q of ST plus 1 comma S dash, I am choosing maximum of Q of ST plus 1 comma A over A. We choose all actions to take the maximum from the state ST plus 1. You just stand on the state ST plus 1 and look around. How many actions are originated from this ST plus 1? So this is ST plus 1. There are 3 actions. Then how will choose this action? Choose those actions with the maximum reward. That is why I cross these actions by an arc. That is an indication for maximization. Sutton doesn't put some max letter along with this representation. Whenever we cross these activities or actions by a curve, that means maximization. Okay. So the updates is happen only with action with the maximum reward. This update happened to those actions with the maximum reward. Okay, at each stage in each step, all the step it will happen, but this update will happen at each step, but that particular action is incorporated only at the end of the episode. That is very important. Update will happen, but we will never choose that action in that episode to that policy. We are not going to incorporate that action with the maximum value, maximum Q value into the policy within the episode. That will happen only at the end of the episode. Okay, now say this is the backup diagram. In SARSA, we just start with an action value, an action from a state yes, then look into the next state, then choose any of this action arbitrarily. We can use epsilon greedy policy or epsilon soft policy. Ultimately, if you repeat this iterative update, it will lead to an expectation. That means at the end of the process, it is just like an expectation, but it is a maximization process. So it is happened at the end of each episode. It is called an off policy. It will not happen within the episode iteration. That is the difference. You just remember this comparative state diagram. Okay, then this is a pseudo code. The pseudo code is almost same. Algorithm parameters, initialize Q of SA, all these are same, but the difference is here. One is updation formula. Q of SA changes to or updates to Q of SA plus alpha into reward plus gamma into max over A Q of S dash A minus Q of SA. Okay, instead of gamma into Q of S dash A dash, I choose this formula. Okay, then in the next update, the state S is updated to S dash. That means we just jump into the next state, but within this episode we are not changing the action A to A dash. That is the difference. We are not changing action A to A dash. If that happen, what happened within the episode, that action will be replaced. When we replace an action within the episode, policy will change. So the policy will same until that particular episode is over. At the end of the episode, this action will be updated. That is happened with the help of this choice. Greedy policy, it will happen automatically. Now just an example for TD control, we emulate the grid world problem once again here. Here this is a start point, this is the destination point or goal. There is a cliff in between the start and goal. That means like a long jump. You have to jump from S and to reach G, so that you will not come into this cliff. This cliff is like a fire. When you jump into the fire, you will be finished. Okay, so there are two options. One is just move away from this fire or cliff, then move over it and leads to the goal. Another one is just to move one step ahead and go over the cliff and reach this goal G. Okay, see here the cliff walking rules are like this. This is a standard undiscounted episodic task with the start and goal states, start and goal state, and the usual actions causing movement up, down, left, right with the reward -1, except in this region cliff. In the cliff region, stepping into this region incurs a reward of -100. See, upward, left, right movement gives -1 reward. It's actually a negative reward. When it is come into the cliff, this agent will get -100. That means by using this awarding of reward, we ensure that this movement along this cliff is minimum. This reward is -100, so automatically the agent will not try that movement. So we prevent movement along this cliff with the help of adding negative reward. Okay, then how this agent will move? When this agent move away from the starting point in the upward direction, automatically the negative reward incurred. Then when he moves top, it gives -1. Again moves one cell up, again -1. Then the topmost cell again -1. So -3 is here. If this agent start from the initial position or initial state to the next state in a single step, just incur a -1 reward. Then it just moves this direction. So this will reduce this -2, -1 plus -1 -2 rewards. again here -1 -1 -2 rewards. So it can maintain 4 negative points using this path. So it is an optimal path. But this blue path is a safer path. It moves away from this cliff, and so it automatically avoid jumping into the cliff. Okay, so this is safer path, this is optimal path. Then how we will solve this problem with the help of TD control? We will see the complete code in our practical sessions. For the better understanding, I am giving the performance of SARSA and Q-learning. So I repeat the game in 500 episodes. In each episode, I repeat the SARSA and Q-learning 1000 times. So I got a plot like this. So in the previous plot, we have seen the negative rewards increases as it moves away. So the safe path is green color, blue color, and optimal path is in red color. I am using the same thing. SARSA is safer, but Q-learning is more risky. It is risky because it is near to that cliff. So now look here, sum of rewards during this episode. In the 0th episode, starting near the that cliff, so automatically it gives -100. Then as episodes increases, then what happened? The rewards goes on -75, -50, and -25. That means negative rewards. Rewards decreases. As goes on the iterations, the rewards decreases. Then why these oscillations are observed in this path? It's just because of our action chosen policy. Here I am using epsilon soft or epsilon greedy control algorithm there to select an action from a state, and therefore automatically there will be some oscillation, some exploration, exploitation mixing up. That is why this iteration. Now look, there is a gap between SARSA and Q-learning stably here. After 100 iteration, there are some fixed distance between these two algorithms. That means the SARSA is superior to Q-learning in minimizing this error. For Q-learning it is around -50, but for SARSA it is -25. That is the reward value, the negative value is here, so it is minimum for SARSA. So SARSA will give better option while applying repeatedly over episodes. So SARSA outperforms Q-learning. It is just because of that exploration options, and also within the state, within the episode iteration. Within the episode we change the action. So the policy improvement happened within the episode itself. Okay, but in the Q-learning it will not happen like that. Only at the end of one episode the state values are updated. The state values are updated, and automatically the policy will be updated with including that new action with the maximum return value or maximum Q value. Okay. Now R learning is not that much different from SARSA. It is also known as expected SARSA. In SARSA we get that expectation effect only at the end of whole episode, but within the episode if you just apply some averaging operation, see the optimizing the average reward, we simply apply the averaging of reward of actions, then automatically that turn to an R learning. R learning has another name, it is expected SARSA. Okay, but expected SARSA, its performance of expected SARSA is not that much good as our original SARSA on learning on policy TD control method. Then advantages of this expected SARSA. Why this expected SARSA is preferred? While expected SARSA update steps guarantees to reduce the expected TD error. That is very important point. We are using expected rewards at each iteration within the episode. At each iteration within the episode. So what happened? It will definitely minimize the TD error. We simply update with average. This average is actually compared to the minimum. So it minimizes the expected TD error, and so it is better within the episode. SARSA could only achieve that expectation taking many updates with sufficiently small learning rate. That is again one more important point. You should choose the alpha is sufficiently small. Then at the end of infinitely many episodes, it will take the same expectation as the expected SARSA will do. Expected SARSA will take the average within each steps in each episode. That's the difference. So the expected SARSA is seems to be better in minimizing the TD error, but its overall performance is not up to the mark compared with our SARSA. So naturally we are using SARSA for on-learning TD control, but for off-learning TD control we are using our Q-learning approach. Q-learning is most popular with the episodic activities. If an action starts and will terminate after some time or 1 or 2 hours, or just like traveling in a flight, we start our journey, the flight is take off, then when this that flight lands on the ground, then only the policy can be changed. Within the flight we cannot change the policy, if so that will create a lot of problems. So until it finish one episode, the policy cannot be improved. Such situations can be managed well with the help of Q-learning. But in our ordinary learning process happen in the classroom. We the learning process happened continuously. Within each time change, a time sheet that will be updated. We change the policies updated. But in some games, especially our Tic-Tac-toe game, chess, etc., each steps this policy will change. Our policy is depending on opponent's move, the second agent's move, and so at each state it will change within the episode. And that is why SARSA models will work well in most of the game situations, like agent movement in certain situations like this chess or card game, etc. Okay, so there are certainly some disadvantages. One is the making agent lazy. We are trying to make averaging the rewards. Instead of looking to the highest value of action, we just look on the average. That is like teaching people focused on the average students. Suppose I am teaching or I am planning all my lessons and deliver my lessons just on average students, then what happen? The top students also come to the average group. Automatically the level of learning will come to a lower level. It will deteriorating state by state. It will happen. That is why it become lazy. The agent become lazy. So the learning level of agent become in a lower level. The second point is, as long as the agent eventually reaches the goal, it will get maximum average reward. See, what is our aim? Our aim is to teach the agent or help the agent to learn so as to get maximum reward. But in each step we are taking the average reward, so automatically it maximizes the average reward. So we fixed on the average, then we try to select those steps to get the maximize that average reward. That is why our expectation reduces to a mediocre level. That is one of the most popular disadvantage of using this expected SARSA or R learning. The concept of after states, that is mainly related to games. A conventional state value function evaluates states in which the agent has the option of selecting an action. See, that is the usual state action value learning. We find out those states in which there are some maximally returned actions. When the agent will choose that action and move along that environment, so automatically it get maximum reward. So we give more importance to the state and actions. Those states which give maximum return and those actions which give maximum return. Okay, but there are some situations we cannot use it. For example, a musical chair game. Initially there are suppose 5 participants and 5 chairs, so there is no confusion. Then music starts, the people run around in a circle. Then when the bell stops, automatically one chair is removed from the scene. Then one person won't get a chance to get a chair. So everyone immediately try to sit on the chair. one person will away from that particular chair. There is a gap, one chair is removed, so he will lose his seat, so he will out of the game. So what happened here? Here the state value is not important. Here what is important? The position move policy. His position is more important. What is next state? How I get a chance for a seat? That depends on the other person or the second agent's move. So position move policy is important. Instead of state value policy, we need position move policy. That is essential in game, especially game development, because it creates some thrills. See, in a musical chair, if all the seats remains as in the same at the initial state, then what happen? Everyone will get a seat. There is no interest, there is no thrill in game. Okay, when we remove two chairs simultaneously, then the probability for losing becomes become high. So automatically it creates the thrill of the game. The state value function used the most board games evaluates board positions after the agent has made its move. See, state value function for game is different from state value function in ordinary learning. In game theory, especially in board games, it evaluates what? The state value function, the board position, rather than the value corresponding to that position. So for example, tic-tac-toe game is an example. It's a very simple one. Say 3x3 matrix like board, so 9 positions like this. So there is a cross and donut representation. The first player choose cross and second one naturally choose the donut. Then once a player got a complete row with a cross or a diagonal or a column or a diagonal with a cross or donut, he will win the game. Okay, so what is the thrill of the game? The first person play the cross, automatically second person play the donut. What is the second person aim? He tried to prevent other person, the cross person, to get a row, column or a diagonal. So these are first he play this position, so the donut plays here, then cross is here, again donut play here because he tried to get this diagonal, that is his aim. So automatically the second time the cross will play here. It's prevent the donut to put his donut here and to come win the game. So it repeats like this. If the agents or the people or the players are very much intelligent, this maximization of minimization process increases. Ultimately it will end in a draw. That happens most often. If both the players are equally competent, then it will end in a draw. It's a very simple game for children. Okay, so see, this is the state. The next position is very important. His place depending on the position. See here, here we have two donuts here. Definitely if this player will play here, then it prevent his movement to complete one diagonal of donuts. So that is a trick. So position move is very important. Okay, and you look this situation. Cross is here, donut is here. Next chance is for cross. He can play this cross here. This is another state. Donut is here, cross is here. Then next chance is for this cross. Cross will play to the left corner. Then what about the output? See, first of all you place here it. Then next X is here. So this is the new state. Also here the previous state is donut cross. Then cross play this position. So it leads to the same state. That means different action leads to same state. Different actions leads to same state. So after state is same. After state is same. But in our usual game theory approach, usual reinforcement learning approach, after states are different, because this is first state and apply an action, This leads to next state is t plus 1. This is another state. Then another action happens. We move on to next state s t plus 2, something like that. But these after state cases, they are same. We count it as a single state. That is the difference in after state idea. After state methods are still aptly described in terms of generalized policy iteration. That means we can use the same policy iteration approach or generalized policy iteration approach that we have adopted in Monte Carlo and also TD control methods. But the difference is that instead of state value function, we have to use after state value function. That is the only difference. You have to choose after state value instead of state value. Okay. So we apply the same algorithms that we have used in Monte Carlo and TD control. Then we got an optimal policy and optimal state values for the model. So thank you. In the next session we will continue with an extension of TD0 method or temporal difference with a single step into n step. We have already set foot for calculating the error, the TD error in terms of coming state error values. We just extend it into n step. It is more general in nature, and we will use some more terminologies in n step temporal difference like TD lambda, then automatically SARSA lambda, Q lambda, etc. That we'll see in the coming sessions. Thank you.